Hello everyone, my name is Yihun Sun and I'll be presenting our research project, Module V, Learning Mobile Object Detectors from Unlabeled Videos. To alleviate the burden of object instance annotations, unsupervised object detection and segmentation proposes to automatically discover objects from unlabeled data. Under the hood, prior works leverage self-supervised features to segment unlabeled images and produce candidate object regions to train object detectors. In addition, other works use motion information from unlabeled videos to learn segmentation of prominent objects in the images. In our work, we propose Module V, a mobile object detector learned from unlabeled videos only. Here, we argue that motion can serve as an effective cue for unsupervised training of instance-level object detectors. And to effectively leverage this motion information, we propose a new training scheme that trains on unlabeled videos to produce a mobile object detector that can run on static images. First, to obtain the initial pseudo-labels from unlabeled videos, we compute the binary motion mask and monocular depth estimates via dynamo depth, which is a prior work also trained from unlabeled video frames only. Then we project the moving pixels to a pseudo 3D space for clustering, which gives us instance-level motion masks to serve as the initial pseudo-labels for learning an object detector. Despite the high precision, the initial pseudo-labels computed from motion information have limited recall due to multiple biases in the motion mask. First, the static objects are absent in the motion segmentation by definition, such as the parked vehicle boxed in green. To recover these static but mobile objects, we propose a self-training stage moving to mobile, which directly trains a single frame object detector to reproduce the initial pseudo-labeled instances. Since the detector cannot distinguish static objects from the moving ones, the static objects are recovered in the model predictions. In addition to the missing static objects, smaller objects are also often absent in the motion segmentation due to their less noticeable motions from further distances away. Since they look sufficiently different than the initially found larger objects, the small objects remain absent in the pseudo-labels even after the moving to mobile training. And for us to recover these small objects, we propose a second self-training stage, large to small, which trains multiple detectors at different image scales and merge their predictions in the end. Since objects become smaller with reduced image scales, the detector trained with reduced scale can learn to effectively recover the small objects in the images. To summarize, we generate the pseudo-labels from initial motion estimates in 3 stages with iterative self-training. First, we compute the initial pseudo-labels from the available motion segmentation and monocular depth estimates. Then, we progressively recover the large but static objects by directly training on the initial pseudo-labels in the moving to mobile step. Finally, we discover the small objects by training multiple detectors at different scales and merging their predictions in a large to small step. With the final set of labels, we train a standard mask RCN to convergence as the final output of our method. Quantitatively, we observe a consistent improvement in average recall compared to the previous state-of-the-art across 3 self-driving datasets and show competitive results on the COCO dataset. Furthermore, on average recall for small objects, Module V consistently outperforms baseline with roughly 2x improvements across all benchmarked datasets. Here, we showcase qualitative results on the Waymo Open dataset. Compared to the baselines on the left that tend to under-segment multiple nearby objects and detect irrelevant regions, Module V demonstrates high precision while drastically improving recall for small objects as shown in the zoomed-in regions. The same trend is also found in both nuScenes and KITTI, where Module V trained on Waymo demonstrates good generalization when directly applied without any fine-tuning. For more results and code, please visit our project page. Thank you for listening.